I'd like to introduce Sean McNunn. He's the Senior Director of Quantum Optimization Solutions at DWave. A little bit about his background. He has over 30 years of experience in supply chain solutions. He started his career in semiconductor manufacturing, where he helped build optimization-based production scheduling solutions. After that, as a consultant, he's implemented multiple optimization-based planning solutions for some of the world's largest and most complex corporations. At DWave, Sean works directly with companies to explore the opportunities and use cases for DWave's quantum technology, where it can help generate significant ROI for their business. So with that, I'll turn it over to Sean.
Thank you, Susan, and thanks everybody for joining our webinar today. As Susan's mentioned, my name is Sean McNunn. So we're going to start with a little bit of why quantum computing is important today. So as we know, as we look at problems that exist in our business context today, some of those problems are very computationally complex. It's possible that we're solving them today with some optimization techniques. It's possible that they're intractable and we cannot solve them. But nonetheless, we know that the problem landscape is changing and evolving over time. Things are getting more complex. Things are getting more difficult to solve. And we have a need to add additional complexity to the problems that we possibly are even solving today or are solving with some great difficulty. We know that also solving these complex computational problems with classic optimization has its issues or has its liabilities or has its fallbacks. First and foremost, oftentimes they can't handle the complexity that is required. You have to plan in different levels of abstraction, possibly at a week level versus a day level, or at a product family level versus a SKU level, and so on, because of the way that the current classical solutions consume resources. We have in a lot of cases, we have an ability to add the complexity that we need to be able to solve the problems we need to. Second and foremost, they take too much time. I remember doing this when we had to plan over the weekend and we had to get the runs out by Monday morning, 8 o'clock. And oftentimes, we're always up against the clock. And more importantly, if anything goes wrong or something needs to be changed, you've lost that window and you're back to your manual mode of planning. And as anybody who's read an article about AI and resources today, we know that our classic computers are consuming way too much electricity, and we're putting nuclear power plants next to data centers and creative ways to increase the power grids. And we shouldn't have to do that. The solution to all of this, from a business complexity, computationally difficult problems or intractable problems, is quantum computing, and particularly quantum computing with DWave's hybrid annealing capabilities. Now, if you've read anything about quantum computing in the last, say, year or two, you've probably seen what is kind of classic over here on the right side, which is what they call gate modeling. What is called gate modeling? Gate modeling is the multi-purpose digital quantum computing capabilities that is the promise of the future. And if you ask anybody who is in the industry and knows what they're talking about, you'll get a mix of range, but this is 7 to 15 years away. When it arrives, we'll be able to do these wonderful things like quantum chemistry and 3D fluid dynamics and a variety of other kind of intractable things that we cannot do today. But we have to wait because the error rates and some other issues associated with gate programming or gate model quantum computing isn't available to us today. As a result, a few years back, or years and years ago, DWave decided to focus on a type of quantum computing called annealing. Annealing is a sort of an energy transformer, energy wave type of quantum computing using the same quantum effects as gate models, so superposition, entanglement, and so on, but very focused on the ability to solve a specific set of problems. In particular, for commercial uses, this is things like optimization problems. And you can see a list here of the types of optimization problems. We're going to go into more detail later on, but workforce scheduling, production scheduling, these hard business problems that are computationally difficult that we can't solve today. Now, I would be remiss if I didn't point out that DWave is also creating gate models. So we are currently the only computing company or quantum computing company in the world that has production level quantum computers available for use with our customers, by our customers. And we will be the only quantum computing company that has both annealing and gate model in the future, but we're under the same timeline as everybody else, possibly a little bit faster because of the work that we've done with annealing, but nonetheless, that's the state of the art from what is quantum computing, gate model, digital, multi-purpose, annealing, available today through DWave and in production but very focused on a specific set of business problems that are very computationally complex. Now, if we look at DWave as a company, I'm going to focus a little bit on just who we are and where we've been around. We've been around for 20 plus years. And as you can see on the left, as I already mentioned, we're the number one or the first commercial quantum computing company to be able to provide services in production for our customers. We're also we are backing all of that up with 20 years of engineering and development. You can see across the bottom here, we're well papered. We've got 260 plus patents, over 240 specific or scientific papers that have been published. And a lot of this information is available on our website. So if you're curious, I would ask you or invite you to go check out our website, do some research, and be able to download some of these papers and do some additional information. The point here is that it took a long time and a lot of Herculean amounts of engineering effort to be able to provide the services that we do to our customers. As you can see here, some of those customers are names that you recognize. So Ford Otosan or Patterson Food Group, NEC, and so on are people that we've been privileged to do business with. Now, across the top is the result of all of that work, a result of all of those patents and all of that engineering work and all of that scientific work to be able to provide us the ability to provide our customers with a complete end-to-end stack. To explain that a little bit more, I'm going to turn the squares into circles, and we'll look at them in a little bit more depth. First and foremost, when we say a full stack, we start with the fact that we create our own hardware. So we are a computer manufacturing company. We create quantum computers. We're in fact on our 6th generation of quantum computers that we call Advantage 2. The current state of the art is 4,400 qubits plus. Each qubit is interconnected with 20 additional 20 qubits, which gives it that power of multiplicity on top of it to be able to kind of make those entangled decisions together. It's not hyperbole to say that we have in production and released for public consumption with our customers the world's most powerful quantum computer available on the planet. Now, we back that up with what we call our LEAP access, or our LEAP API. LEAP is nothing more than our ability to say, allow our customers to submit a problem to our resources and then get an answer back. It's the API that's, it's backed up by AWS kind of services, but our customers will essentially formulate a problem, submit it through LEAP, we'll take it, and then we'll process it and send the information back. Power of LEAP is that we're at 99.9% uptime. So this is highly reliable, highly available quantum computing at the state of the art. The third pillar or leg of our full stack quantum computing is what we call Ocean. This is the SDK. So think of Ocean as the open source Python available through GitHub set of libraries and tools that allows our customers to be able to build their own quantum applications and submit those problems through LEAP. And then finally, rounding out the entire stack is our launch capabilities, which is really our professional services. And we've come up with, or we've developed over time, driven by our customers, a very easy to adopt, a very easy, low friction entryway into be able to use quantum computing in their business to be able to solve those very highly computational complex problems. We have our computers staged throughout the world. We've got a series of them in Burnaby, Canada, where our R&D and labs are. So multiple systems online available for access via LEAP. We have one in USC in Marina Del Rey. One has just become online in Huntsville, Alabama. And then we sold a system last year to Jülich, Germany. This map is a little bit out of date because we've just recently announced that a new node is going into Italy. And our expectation is that by the end of next year and the years to come, this will become much more dense. So on top of the full quantum computing stack, it's available globally. And with the LEAP capabilities, our LEAP API, we take care of the load balancing. We take care of where the problem gets to be surfaced to or sent to be able to solve. Now, what does that look like to you? If you're a DWave customer, here's how that stack, that full quantum computing stack, comes to life in your environment. On the left side is just an image of what your environment may or may not look like. You have a series of applications that are providing value to your corporation today, whether that's SAP or Oracle. You may have planning systems like OMP and so on. Inside your firewall, you can access through GitHub our Ocean SDK. And through Python, you can build your own quantum computing applications. So you can define how that problem should look in your business, the way that your business needs to run. And you do so inside your own security bubble. None of that information is going to, well, the only information that comes out of that when you call Leap is the actual mathematical formula. So think of it this way. If we're doing a production scheduling problem, for example, part of that problem might be resource constraints. And those resources have names, and they do work on products, and those products they have different rates for those products. The numbers will come through when you call Leap to be able to solve the problem, but the labels stay behind. The contextual information stays protected in your firewall, and all DWave ever sees is the mathematical statements, which makes it nearly impossible for anybody to derive any intelligence from that. So all of that information stays with you. You don't have to worry about internet security or cloud security. It's your data, it's your information, your labels, your contextual information. And we receive the math problem. And then we solve that math problem using our hybrid solvers, which are a combination of solving parts of the problem or the problem on GPUs and CPUs, as well as our quantum computers, which we call Advantage, which we just talked about. The solution is identified and the information is sent back, and then you post-process it and add back to that mathematical result the contextual information that gives you the business value that you need. Now, I brought up a new term in that last slide called hybrid solvers, and I want to explain that a little bit better. When we solve an optimization problem, we have a series of hybrid solvers. The latest and greatest is what we call our NL solver, or nonlinear solver. And when we've constructed this, we've actually built it out to take advantage of the best of all possible worlds. So using standard classical mixed integer linear programming, we can use CPUs and GPUs. And if the problem is formatted in a way that GPUs and CPUs can solve it, standard and MIP programming, then of course we will solve it that way. The Ocean toolkit takes care of that for us. You don't have to worry about it. We just use that capability as part of our NL solver stack, or a hybrid solver stack, to be able to solve those types of the problems. Now, in addition to that, because we're DWave, we're the only ones in the world that have quantum optimization in addition to mixed integer linear programming. That takes advantage of all of the things we've been talking about today, the 4,400 qubits interconnected 20 different times and so on, and lends itself to being able to, in addition to mixed integer problems, be able to solve those natively non-convex types of problems, right? So this is where the power of our quantum technology plus the power of classical technology are fused together to give you the ability to solve those types of problems and more importantly, represent things in a nonlinear way, which in the way that if you've done this before, oftentimes we have to linearize constraints, linearize variables when we don't really want to because they're not naturally linear. We've added to that nonlinear solver then two additional key pieces or pillars of capabilities. The first one is the ability to use lists, sets, and other combinatorial variables in the actual problem construction. So there's not very many commercial solvers available that allows you to do this. And what that means to us as business users is it allows us to actually make the problem smaller and simpler, but also make it look more like the real world problem that we're trying to solve. Instead of having to construct a whole host of linear variables to account for a nonlinear relationship, we can actually just formulate that in a list and formulate that in a sys, or formulate that with our nonlinear solver. And then finally, the last stack in our nonlinear hybrid solver is tensor programming. Most people think of tensor programming as a ML kind of capability, and it is. We use it to create those n-dimensional arrays, which allows you to, again, formulate the problem in a way that is closer and more native to the way that the problem actually looks. All of this combined together gives us sort of a first in class or best in class solver capability that takes into account the best in class quantum capability plus all of the other pillars of optimization combined into one. And because we're modeling the problem in a way that makes a lot more, or is constructed in a way that looks more like how the problem is natively appears to us, you get the ability to be able to essentially change and adapt and keep the model evolving over time as your business evolves. Switching gears, and let's talk about some solutions now. Let's talk about how we can use that technology stack, all of that capability that we just talked about with the NL solver, the hybrid solvers, quantum computers, Leap Access, Ocean Toolkit, and so on. When we go to a customer and start working with them on opportunities and use cases and types of solutions that quantum computing can benefit for them, we look for solutions that will be able to provide value across these 4 different dimensions. And it doesn't need to be all 4, but certainly value across dimensions that we can quantify across 4 different elements or constructs. The first one is the time to answer. So, and this is important from a quantum computing point of view. Getting that first answer is typically, is significantly faster. And you'll see that in some of the examples that we're going through. So we can take processing times for that entire solve pipeline from, hours down to minutes. And it allows you to be able to construct that first problem very, very fast. But more importantly, it allows you then, because of the increased time or decreased time or the speed at which we're able to solve, we're able to then to resolve that problem. My kind of favorite phrase is, the great philosopher Mike Tyson said, everybody's got a plan until you get punched in the mouth. And we see that happening today in all of our use cases. Production plans need to be resolved or re-optimized because a piece of tooling went down. Logistics plans need to be re-optimized because there's traffic flow delays and so on. So the ability to solve the first plan faster and then resolve subsequent optimal plans on top of that when natural events happen to be able to disrupt that. The second criteria that we look for is when we need to have a higher quality of answer. And by quality of answer, I mean we're able to take into account more or additional variables or take the problem at the level of detail that is required to solve it for today's situation. A couple examples of that. And I think I've already mentioned these. When I was building some of these solutions before in different industries, we had to plan at things like a family level as opposed to a SKU level because we couldn't accommodate for all of the detail at the SKU level. Or we had to plan at weeks as opposed to days because we didn't have enough essentially resources to be able to plan at the level we needed to. So we can take that level of detail and add it back into the problem, solve things the way that we want to, and provide through quantum computing, through DWave, a higher quality of answer. And we look for those opportunities. The third leg is the lower cost of answers. And this implies not just in the energy costs, which we've already talked about, and we'll spend a little bit more time on later, but also the ability to maintain the solution long-term. So the cost of ownership of your overall solution goes down significantly because we're modeling the problem closer to how the business thinks of it, because we're using a standard open source toolkit that's extensible by you. You don't have to linearize things that aren't linear and so on, and you can make that problem look that way you want to. And it makes the overall cost of ownership significantly easier. And then the fourth pillar is kind of a symptom of the first 3, but the ability then to be more agile in your planning processes, to be able to replan when you need to be able to do what if scenarios when you need to be able to add constraints, add variables, change the way that the model works in order to accommodate the fact that your business has just recently changed. If we see opportunity across one or many of those pillars, we know that that's a reasonable opportunity or a good target for quantum optimization. And we know that we'll be able to deliver significant value to your organization. Here's some use cases that we typically talk about. Now, this is by no means an exhaustive list. This is just a illustrative list that kind of looks at a generic type of supply chain. So kind of reading from left to right, if you think about a classic supply chain, and I know that this probably doesn't represent anybody exactly, but you've got raw materials. Those raw materials may be supplied by a supplier, but you've got suppliers that might be supplying those as well as sub-assemblies and so on. So on the front end of the supply chain, you're dealing with materials, you're dealing with suppliers, and there's optimization opportunities around how do I spend with those suppliers? How do I optimize my spend with those suppliers? How do I optimize my replenishment problems and so on? When you get into the production, now you're dealing with things like scheduling or inventory optimization. So if I kind of look at scheduling, I look at scheduling across 2 sort of flavors of it. There's master production scheduling, which is planning that network. So I've got multiple ways to make my products, multiple facilities that can make the same products, maybe multiple ways to distribute it. I've got demand coming in from omni-channel. And master scheduling gives me the ability to solve that entire network and optimize that. Now, the reason this is important is we know based on today's situation that things are happening. So tariffs are happening at my overseas facility. I need to move volume somewhere else. That's now become more expensive. Maybe a shipping lane has been shut down because of a tanker blew up the Suez Canal. So I need to be able to accommodate that and reroute the flow of my goods outside of that particular traffic lane. All of those either black swan events or the day-to-day events force me into a situation where, with today's complexity, I need the ability to model or have in my optimization model some of those constraints, but then more importantly, replan and re-optimize around that to get me back to that optimal plan that I want to be if things go wrong. Similarly, on the production scheduling side, we're now taking that plan and we're going down to a daily shift schedule, maybe even an hourly shift schedule, where we're looking at things like setups. We're looking at things like run rates and planning at the SKU level and so on. Those additional levels of complexity is a different type of problem, but it forces us to allow for additional constraints. Maybe I want to include labor because that's a labor pool is becoming more and more significantly tight for my type of resources, or the cost of opening up a new facility, or the cost of overtime, or the cost of energy needs to change, or I need to model it differently than I did before because I've got new and different sources of energy, for example. So being able to plan and adjust at the more complexity level and faster for production scheduling is inherently required and is part of that computationally complex business problems that we solve. Moving a little bit further down without draining this entire slide, as we get to the point where we're looking at finished goods, we need to distribute those things out. Sometimes we distribute it from my factories to a regional DC, to a final DC, to a retail outlet, or to a customer, if I'm an OEM, and so on. But what we've seen lately, or what we're talking to a lot of customers, is that routing problem. Just the solution or the complexity associated with what trucks go where, how many stops do they have to make, how do I minimize my gas consumption, how do I minimize the amount of hours or miles spent on the road, is becoming more and more important. We're introducing EVs into that mix. They have a different type of construct. They have a different set of constraints that we have to be aware of, like recharging at different points versus just filling up at a gas station and so on. So the complexity is increasing. And some of our conversations with some of the largest logistics companies in the world are saying, we know how to solve these problems. They have been around for a long period of time, but today they're becoming more and more difficult. They're becoming more and more intractable, and that we can't solve them the way that we need to in the time frame that we need to with the complexity that we need to. So quantum computing becomes an option for that. Similarly, on the front end of that, the truck loading. And I admit that I did not know that this was a large part of an optimization problem before I started talking to some of these logistics customers. And it is sort of the A and the B, or the yin and the yang, or the front and the back of that whole logistics network. So not only do I want to optimize the network and the trucks and the routes, but I need to optimize how I'm filling those trucks up. And in today's world, a hot order drops down, a large order drops down, somebody cancels. That information is changing on a real-time basis. So the need for speed, the need for the ability to replan, and the need for the ability to include some additional complexity comes into play very deeply there. And finally, as we move down further into the supply chain out to the customer side, we see that we have things like the ability to, in consumer goods, maybe you have a promotional optimization where I want to shape demand based on offering promotions. And you see these every day when you go to the grocery store or when you buy things online. It's a discount today. It's a BOGO today. If you're a retailer, maybe you're getting a bill back based on how much volume you're buying if you commit to a certain level, and so on. All of those activities cost money, and that money has to be budgeted for. So how do I optimize the amount of spend that I want to introduce into the promotional world? What types of promotions do I want to do to be able to make those promotions the most efficient and the most effective? There's a corollary on a services industry where you may be talking about offer optimization or offer promotions, where maybe a credit card company is offering different types of credit cards with different interest rates to different demographics, but similarly constrained to things like budgets and so on, that you can't offer everything to everybody. You need to make sure that you're spending that promotional dollars or that offer dollars in the correct ways. So again, not an exhaustive list, but if you think about your business and your supply chain and that end-to-end from production to logistics, starting with suppliers and so on, there is a plethora of these computationally hard or complex business problems that we need to be able to solve better in terms of speed, in terms of complexity and accuracy or better answers, and in terms of a lower cost type of solution. The way that we engage with our customers, and this is sort of a journey that has been collaboratively dictated to us by our customers. Quantum is new, and we want to make sure that we're not asking our customers to invest or have a leap of faith. We want to work with them in a way that we are positioning this so that we're proving things along the way. So we start typically with the discovery process. And the discovery process is similar to any discovery process where we understand what are the different use cases, what are the different opportunities that you are, or challenges that you're facing around those computationally complex problems in your world. Is it logistics centric? Is it manufacturing centric? Is it supplier centric? Or is it all of the above? Along the way, while we're learning about your environment and your opportunities, we're doing our best to make sure that you understand what quantum optimization looks like. What types of opportunities looks good for quantum optimization? Because they're not all going to be great. Some of them might just be workable on the classic solution, in which case, stay with it. And we'll do our best to make sure that that's very clear. So the learning goes both ways, understanding your business, you understanding what we can offer to your business. And then we go through a collaborative effort where we prioritize, analyze those, understand what's the level of effort versus the amount of business value that we can deliver. And from that, we have a plan. That plan might be multiple use cases that we want to jump into, but we'll always have a starting point that says, let's start here. Once we have that plan, we go through a 3-step implementation process. The first one is a POT, or proof of technology. All we're doing in a proof of technology is making sure that you understand, or that the problem is essentially solvable in a quantum optimization solution, right? So we want to demonstrate that the technology is feasible. We want to look at maybe a subset of the constraints, maybe a single data set, but it's to give both of us comfort that yes, optimization will work from a quantum point of view in this particular problem in your business, and we understand what the value is going to be because we now refined it a little bit further. We then move into a proof of concept. Now, proof of concept is really where we're developing that final solution that hopefully goes into production. So we might try different formulations. We might look at different data sets. We're looking at the entire picture to say, have we accounted for all the corner cases? Have we accounted for all of the types of nuances that are required, the variables and constraints, so that when we go live with this, we are confident together that it will drive the ROI that we're expecting to be able to get. We can quantify and calculate that at this point. When we enter the pilot phase, we're just perfecting that pipeline, right? So up until this point, we've really kind of been focused a lot on the math. When we get to the pilot phase, we want to focus on, is this production ready? And if not, what do we have to do to get there? So the data pipeline that's inside your firewall, is that bulletproof? Is that ready to go? Is that fault tolerant or air tolerant? Yes. Do we have the pipeline that goes, calls the leap system and is able to solve the solution? Do you know what to do when it comes back? Do we know how to feed the downstream systems with the results and so on? So perfecting that entire pipeline, and maybe looking at it from, a subset of products or a subset of areas sometimes makes sense as well. And then finally, the goal is to put these solutions into production. These are your quantum applications we've developed with you using our launch capabilities and your internal resources. And now you have the ability to say, I want to go realize that value that we've calculated along the way as we've discovered it, and then evaluated it in POT, perfected it in the POC, demonstrated it in the pilot. Let's reap those benefits. Let's get that ROI that we want to, and put the solution into production. So that journey is how we work and engage with our customers. And again, we've designed this largely at the customer's direction, but it's meant to be the lowest possible risk for you to understand how quantum optimization, DWave's quantum annealing capabilities using our hybrid solvers can add value to your business. So I want to switch gears now and talk a little bit about some case studies. These are a couple real-world examples. As I've hopefully mentioned a few times, and hopefully it's been clear, We are the only quantum computing company in production today. We have live customers using our solutions, using the solutions that were created for them on a day-to-day basis. One of those is called Pattison Food Groups. Pattison Food Groups, if you're from Canada, Save On Foods probably is very familiar to you. It's a very large grocery store, grocery chain. And the problem they were facing was creating a schedule of their drivers for their logistics for their drivers, the driver scheduling problem. Now, this was an incredibly cost sensitive problem because the people that were doing it manually were typically managers. So they were the more expensive side of the resource house. They were taking a great deal of time to be able to do it. They weren't able to take into account a lot of the resource constraints that they wanted to be able to because they simply just did not have enough time. And so they turned to DWave, and using quantum optimization, they were able to turn this from or basically take 80% of the time that it took to create these schedules off and be able to do it in 20% of the time total. Now, what this means to us, if we think back to where the quantum benefit lies, clearly it was a faster time to an answer. We reduced it by 80%. Clearly it was a better answer because which is not called out specifically here, but we were able to include constraints, able to include nuances in that labor pool that they weren't able to account for before, like maybe a union rule or maybe a skill set matrix or things like that. They said, now I've got a better answer because I'm able to include additional constraints that I wasn't able to before. They can maintain the solution, so their cost is going down, not only from a long-term cost of ownership, but those expensive resources that we're spending a day and a half to create these plans are now able to go off and add or work on more value-added activities. And the last pillar that we talk about oftentimes is, their agility. So now, because it's so much of a faster generation of the plan, when something goes wrong, somebody doesn't show up to work, or there's a significant delay in the actual logistics process itself, they're able to take that plan and regenerate it quickly. Another use case is Ford Otosan. Ford Otosan, if you don't know, is a joint venture between Ford and Hakkak Holding in Turkey. And this is a body shop scheduling problem. So a body shop think of it as inbound bodies are coming in to get painted and get processed. So those bodies might be your car bodies that are 2 doors versus 4 doors, or left hand versus right hand, or larger van bodies or bus bodies and so on. So a variety of different types and configurations with different attributes are coming into the body shop. And the scheduling problem is, how do I minimize my overall setup requirements? Because I don't want to be changing over every single time. And that's an easy enough thing to do. I could, get a spreadsheet, list 1,000 trucks, sort by attributes, and minimize setups. But in addition to that, they also wanted to make sure that things were linear. If I just optimize to setup reduction, I may have big spikes of work in one particular time frame and little shallow pieces of work in the other time frame, and that causes all sorts of problems when it comes to scheduling staff and so on. So getting a more linear plan out was an advantage. And then the third big opportunity for Ford Otosan was the ability to add additional constraints and be able to tweak those additional constraints to rapidly do a what if and rapidly change things. So what if I wanted to have the system schedule no more than 4 jumbo trucks in a row, because then I have to go back to cars? What if I change that to 5? What if I change that to 3? What if I tweak those parameters as additional constraints? And then see what that implement is going to be to my plan, how many vehicles am I going to be able to get out, and so on. So again, think back to those 4 lines that we talked about, a faster solution. So we're able to take their production scheduling time for 1,000 vehicles from 30 minutes to 5 minutes. So the initial problem solved faster, but then the agility comes into play because they're able to replan, slide things around, change some of those parameters, and see what the impact is from a what if perspective. They're getting a higher quality result or a higher quality answer because they're able to take into account some of those additional constraints that they weren't able to before. And their solution is now something that they can maintain and add those additional constraints to as they go forward. So it's a lower cost of ownership for them as well. So in summary, I just want to bring us back to this whole idea of quantum realize. We started with talking about that there are computationally complex problems out there. We know that classical computing struggles with those from a complexity point of view, from a time point of view, and from an energy consumption point of view. And the answer is quantum is realized today. Quantum computing for optimization problems is available today in production, as demonstrated by the use cases that we just talked about. And there's three dimensions when we say quantum realize. First and foremost is performance. Hopefully you understood from the use cases, going from 30 minutes of scheduling times to 5 minutes, taking 80% off of the production scheduling time at Patterson Food Groups and so on. So in real world examples, in commercial uses, we've seen significant performance, and we've been able to measure across those four dimensions of value that we talked about. There's another study, which is we just released last year, which is our quantum supremacy paper, which is published in Science. And that's what's being referenced here with the nearly 1 million years. This is not really a commercial problem, but it's kind of fun to talk about. It's called a spin glass problem, which is magnetic properties in a matrix and so on. The essence of the problem is there's a computer named Frontier at Oak Ridge National Labs, and it was estimated that computer, which is a supercomputer, I think the second or third, one of the largest in the world, would have taken over 1 million years, or nearly 1 million years, I should say, to solve this problem. DWave, using our existing quantum Advantage 2 quantum stack that we just talked about, was able to solve it in 20 minutes. Additionally, the amount of energy that would have predicted or expected to be consumed during that nearly 1 million years was the amount of energy that's produced on the face of the Earth in 1 calendar year. DWave was able to solve it in less than $1. In fact, I think it was 77 cents, as one of my colleagues calculated. Right? So not only do we have highly performant systems that deliver business value, as evidenced by the use cases, as evidenced by this case study, but we do so at an incredibly energy efficient level. And when I say incredibly, it's just phenomenally small amounts of energy is required for us to do the compute that we need to. The second axis that we look at when we say quantum realized is reliability. We've talked about it a little bit before, but we're at 3.9 performance level through our leap access, which means that in production, you have 99.9% confidence that when you submit your problem, it's going to be received, accepted, solved, and sent back to you. Other quantum providers can't say the same thing. It might take days, it might take weeks, it might never come back. You never know. Their uptime is in the 20%, 30%, 40% type of range. We're at 99.9%. We're highly reliable, extremely performant, low energy compute. And hopefully, as we've demonstrated here, we are commercially available. We're the only system in production, or the only quantum computing company in production. We have live customers. You saw a couple examples, solving business applications, adding real value to their organizations today. So where do we go from here? We can talk about a couple of different steps. The first one, if you'd want to continue this conversation or go into more depth with anything, please scan this QR code. We'll get back in touch with you and then figure out where we go from there. It might be as simple as a follow-on conversation for some questions you might have had. It might be as exciting as, let's enter into one of those discovery phases and let's look at your organization and identify where the opportunities might lie. So by scanning the QR code, that's a way for you to reach back out to us and we can get in contact. And the second thing as a follow-up is we have our user conference in January, late January, in Boca Raton, Florida. Now for this, I'm going to ask Susan to jump back in and give you a little bit of story about why this is important, some of the exciting things that are going on at Qubits 26 in Boca.
Let me tell you about Qubits. This is number 13 for our annual user conference. They typically move all around the country, sometimes in Europe as well. We did our first Qubits Japan this year. So this two-day conference is really focused on kind of two different tracks, one of which is business and applications, which has always been an area for us that we really excel at. And if you come, you'll hear plenty of great, interesting projects from our customers, including those production applications, how they got there, what their goals were, how it's going, that sort of thing. There's also going to be an enhanced research track this year. So you'll really hear some of the greatest research going on from researchers around the world, both at DWave and externally. And we really think it's a great opportunity. There also will be a 2-hour programming class, working on using our NL solver to solve optimization problems. And you can attend that as well. So a few ways you can participate. If you go to qubits.com, we'd love to have you come in person. Beautiful resort, great time of year to be in Florida. If you're unable to do that and get to Florida, the first day of the conference will be streamed live. So all you have to do is go to qubits.com and either register for in-person attendance or for day one, the virtual attendance. So we hope you can do that. One thing we want to do before we go to questions is we have a few questions for you. So let me launch this poll, and if you would take a minute, we are always interested in finding out what else would be important for you to learn about. As many of you know, we do webinars just about every month. We tend to vary the topics so that we have both DWave presenters, third-party presenters. We talk about business applications, we talk about research, we talk about technology. We did a very interesting one, I think it was last month, on how to recognize good problems for quantum. All of the DWave webinars are then recorded and put on our YouTube channel, so you can take a look there if you've missed it. For those asking about the recording of this or slides, we will send out an email in the next few days to everyone who registered, and with a link to the slides and the recording. So let's see if we have a few more seconds, and then we'll move on.
Susan, I noticed that I can't click excellent. For some reason, you won't let hosts evaluate themselves. That's unfair.
Yes, I'm very sorry, but we'll see what everyone else says about you. So, all right, I'm going to end the poll. Thank you very much for everyone who attended, everyone who answered. Now we're going to get to Q&A. So I'm going to ask Ken Robbins to come on camera. Ken has been a panelist for us, which means he's been in the background answering questions as they come in. We've had quite a few questions that he's answered, but we have quite a few more that we'd like to ask our presenters out loud. So first question, we are seeing generative AI, especially LLMs, being increasingly used to solve combinatorial optimization problems. How does quantum annealing-based solutions compare with LLM-based solution times, and quality-wise, have you done any benchmarking studies? I don't know if either of you know enough about that to answer.
You want to go, Ken, or you want me to?
I have suspicions. So specifically using LLMs to solve combinatorial optimization problems, okay. I should preface by saying I'm not a guaranteed expert on this. I don't think we have done any dedicated benchmarking studies, or if we have, I haven't heard of them. But I suspect that certain combinatorial optimization problems, when you're using generative AI, I mean, it's sort of like a pattern finding thing, right? It works in situations where it would work in situations where the landscape is somewhat predictable, like the problem landscape is somewhat predictable. I imagine that in highly intricate problems, where there's a very complicated high gradient areas in the like problem landscape, the energy landscape that we talk about, I imagine we would pull ahead, but I can't say for sure, as I have not done any benchmarking. I apologize.
Okay,
No, I
Sean.
agree that we've definitely not done any benchmarking in that space. I'm a little bit suspicious of LLM AI models being optimal. I think they're predictive, of course, but actually solving to an optimality is I'd have to look into that a bit more. But we're able to help generate and help train AI models from using RVMs for sort of image recognition and sort of behind the scenes, like the engine behind the scenes, but not native language.
Okay. First of all, Sean, your audio is kind of cutting out a little bit, so I don't know if there's anything you could do about that. Next question. We had a few questions regarding pharma applications. For a greenfield pharmaceutical R&D center planning to integrate DWave quantum annealing with classical HPC infrastructure for drug discovery applications, particularly protein ligand binding optimization and molecular conformation sampling, what would be the realistic time frame from contract signing to achieving production-ready hybrid workflows? More specifically, what are the critical dependencies in terms of problem reformulation expertise, middleware development, and on-site support that we should account for 36-month implementation roadmap?
Oh, 36 months. Okay. I thought you were going to say like 6 months.
Yeah, I will say, by the way, that we do have customers actually who are doing drug discovery, which we'll be presenting at Qubits. But Sean or Ken? Any
I
guidance
mean, my
there?
short answer to this, Ken, you can elaborate, is this is one of those, like, let's have a deeper conversation type of questions. There's almost no way to, sort of answer that, like, definitively based on that description, but I would love to actually go into more depth and understand exactly what's going on. But we have experience in drug discovery, as Susan pointed out. We're more than happy to jump in and formulate that and understand and give you the answers you need, but I don't think we can give it to you from, as a shoot from the hip type of a thing.
Fair enough. Let's just keep going. Question for network design, optimize bandwidth utilization, placement of nodes, network virtualization. I guess the question is, are those good problems for quantum?
Placement of nodes, yeah, that's an easy one. Bandwidth utilization sounds good. Network virtualization, I'm not actually sure about, but in that I don't know what it is. But the other two sound good, yeah.
Okay, and we do.
Yeah, and even in the example of NTT Docomo is essentially network optimization as well. Packets across the network, and so yes.
So regarding that, so NTT Docomo is one of our customers who is using our technology in production. There is a case story. If you go to our website and you go to applications or the resource library, you will see what we call a case story about NTT Docomo. They also had presented at Qubits last year. So there's presentations on our YouTube channel about that as well. But I think that would apply certainly in the telecom space. Here's a question which actually I think we answered in one of the recent webinar I talked about, which we called quantum fit, but I'll ask it again. Hello, among the problems mappable onto a QUBO, what type of problems seem to be well suited or badly suited for the DWave solvers? High number of constraints, high number of variables. I mean, some problems have a bad number of variable conversion from classical formulation to QUBO formulation. Are there criterions like this, size, connectivity, variable scaling, or do we test every problem to know?
So QUBO formula, first off, these are absolutely correct intuitions, is that there's often a high overhead. What I will say is that our hybrid tools in general abstract that away for you. So you don't really need to worry about any of that. You can basically type your problems symbolically, not even thinking about having to decompose into a QUBO format. Although it does work very well if it is a nice QUBO problem. The limitations that you run into are reasonably, as you might expect, the ones that you suggest, like the number of, if there's a lot of variables, that's good. We tend to pull ahead of classical solvers with large problems, but with our largest tools, we can only handle roughly 2 million variables. You go beyond that, we're probably not going to be able to help you unless we reformulate. And lots of constraints in general, yeah. Not like an overly constrained problem where there's like a similar number of constraints as there's variables, which I have seen. But in a lot of our successes come from places where the customer is unable to represent all of the constraints they want on a classical tool. It's just not providing the proper solutions anymore, and we are able to jump in and fulfill that.
Okay, and
yeah.
One more plug for Qubits. We will kind of reprise the webinar that we did.
Yeah,
and there'll be a talk on that as well, and our professional services team that actually does all this work with companies will all be there as well. Next question, are these use cases documented in tutorial-like format for a beginner to get an understanding?
So
the ones that I presented.
Sorry,
Is
Sean.
that the question?
Go ahead, Sean.
Oh yeah. So the short answer is kind of yes, right? So for every use case that we propose to a customer, as well as any use cases that come out of discovery, we document into what we call a canvas, which is the problem statement, the objective statement, what are the decision variables, what are the constraints associated with this, who are essentially the stakeholders, what is the data required, and so on. So we summarize that and do document them that way. The ones that are generic, it's sort of, here's a generic production scheduling problem. We're more than happy to share in a conversation with you. The ones that are specific to a customer that have come out of discovery, of course, those are not terrible, but short answer is yes, we document them across the entire solution.
Okay. Can you tell the mechanism how you deal with constraints in quantum computers?
So on the QPU level, it's essentially a penalty mechanism where it's the idea that when you write in something, the objective function, where you say, if we don't satisfy these constraints, we move further away from the optimal solution. On the user level, especially with our hybrid tools, we've kind of just abstracted that away. There's basically just an add constraint function that you type in your constraint and it will figure out a way to put that constraint into your problem.
Okay, let's see, we've got just time for a couple more questions. Let's see. Does the problem need to match the DWave architecture for computation, problems that are amenable to quantum annealing? So if I want to study the collision of two black holes and see how the event horizons merge in time, that might be solvable with DWave.
So, okay, I'm a former cosmologist. I have some experience with gravitational physics. No, it's a bad fit. Don't do it. Gravitational radiation, all general relativity, all that stuff is differential equations. It's all differential equations all the way down. Differential equations are not a good fit for DWave. It's not that we haven't shown, we don't have anything saying that they are bad forever. It's just that we have seen zero evidence to suggest we're going to be competitive at solving them. Maybe we'll figure out something someday, but currently there's no suggestion. So yeah, I would say that if you're trying to do space-time calculations, don't do it.
Sean, someone asked to share the previous QR code again. So if you go back to the slide that had the QR code for.
Yeah. Oops, there we go.
Yep, great. Thank you very much. All right. Let's see if anyone can answer this. For the Japan tobacco de novo protein work, what was the typical problem size and number of qubits variables, and how did you structure the classical quantum workflow? Specifically, did they use hybrid solvers or pure quantum annealing? And what was the speed up compared to classical generative models? And before anybody, I don't know if Ken, you know enough about it to answer. We are also hoping that Japan Tobacco will come to us this year and give us an update on their work, but we're waiting to see if that'll happen. But so, Ken, is this something you're?
Yeah, so I can only talk about the what was made publicly. It's ultimately a hybrid workflow, but they built their own. They're directly sampling from our QPU. They're not using our proprietary hybrid tech. There wasn't so much a speed up, I believe. There might have been, as much as there was a quality increase. The solution quality shot up across 3 metrics when they replaced the tool they were using with us. And as a result, we were basically just being used as like a replacement sampler tool in this pipeline. And it was, I believe the 3 metrics were, one of them was size. So it was like, it was just smaller. They were trying to look for smaller molecules to be able to pass through cell membranes more easily. I'm afraid I don't have any information like number of qubits. I know that it's not as simply straightforward as like an optimization problem where you define each qubit representing a decision variable, because it was essentially using the computer to create useful probability distributions as opposed to almost defining a problem directly. It's a little bit more subtle than that.
Okay. Well, with that, we are out of time now. So I'd like to thank everyone for attending. I'd really like to thank Sean and Ken for all your great work today. As I said, we will send out emails with a link to the recording and to the slides. And we hope you can come to Qubits in one way or another. And we look forward to seeing you at a future DWave webinar. So thanks very much, everyone. Take care.
Thank you all.